Hello, this is Miss Moore, and today we're going to continue discussing periodic trends, specifically valence electrons. Today's essential question: how is the organization of the periodic table related to electron configuration? Make sure you answer this essential question in your summary. Okay. Elements are arranged in periodic table in order of increasing atomic number. That in and of itself is a periodic trend, right? We have hydrogen, which has atomic number of 1, and then helium, lithium, beryllium, boron, right? The arrangement of the periodic table reveals other trends or general tendencies in the physical and chemical properties of elements. Okay. So let's talk about specifically the electron configuration and the periodic table. Okay. We have valence electrons, which are the electrons in the outermost principal quantum energy level. That's huge. Energy level of an atom. And the core electrons are the inner electrons. So if I were to draw the electron configuration of, let's say, I don't know, we'll pick carbon. We have 1s2, 2s2, 2p6. The valence electrons are the electrons in the outermost principal quantum energy level. Remember, energy levels are represented by numbers. So those are the valence electrons. Those are the core electrons. The periodic table can be divided into sections or blocks that correspond to the sublevels that are filled with electrons. So the first block we have is the S block. The S block contains groups 1, 2, and helium. Okay, so the S block are those right there. The reason they're called the S block is because of the valence electrons. So if we look at hydrogen, hydrogen is 1s1. Lithium is 1s2, 2s1. Sodium, 1s2, 2s2, 2p6, 3s1. So the valence electrons for all of the first group, group 1, are s1. So we've got here, this is helium ends in 1s1, lithium 2s1, sodium 3s1. So potassium would be 4s1, rubidium would be 5s1, cesium would be 6s1, and francium would be 7s1. Okay, if we now look at group 2, beryllium is 1s2, magnesium is, beryllium is not 1s2. I so lied to you. Let's try that again. Beryllium is 1s2, 2s2. Magnesium is 1s2, 2s2, 2p6, 3s2, and so forth. So all of group 2 ends in 2s2. Okay? And helium's a special case. He is 1s2, but he's over there with the noble gases. All right, so we've got the S block. Next, we have the P block. P block contains groups 13 through 18, or 3A through 8A. Okay, so everybody in group 3A ends in 3s. No, not 3. Sorry. Let's try that again. Everybody in the group 3A ends in something s2, and then p1. Everybody in 4A ends in s2, 2, p2. Everybody in 5A ends in s2, p3, and so forth, all the way up to the noble gases, which end in s2, p6, all of them except helium. All right, so that's the P block. Next we have the D block. The D block is this area right here. And for the D block, we can't exactly say that the valence electrons end in D, because these poor guys can never be valence. And let me show you that real quick. So if we take, for example, scandium, we're going to have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. All right? So the valence in this case is going to be 4s. But the last thing we write is 3d. Okay, so the D block, we end up feeling electrons in the D, even though they're not the valence. So these guys here end in 3d1, 3d2, 3d3, etc. However, when we're talking about valence, all of these guys, valence electrons, are going to be s2. These will be 4s2, 5s2, 6s2, 7s2. Okay. Last we have the F block. The F block is right there. And if we continue with the same pattern, these guys will end in F1, F2, F3, all the way up to F14. And again, even though they end up filling in F last, F can never be valence, so their valence will still be S2. Abbreviated configuration. So abbreviated configuration is kind of nice. It's a shorthand way to write electron configurations. What you do is you write the symbol for the noble gas near, just before the atom, and then you just write the valence electrons. So you don't have to write every time 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 4p6, and so forth. Okay, so let's try one. Let's say I wanted to write the electron configuration for sodium. So sodium is 1s2, 2s2, 2p6, 3s1. The noble gas, this is the long form, normal. If we wanted to write the abbreviated version, we go back and find the nearest noble gas before sodium. Sodium is element number 11. Neon is the nearest noble gas before sodium. So we would write neon 1s, no, not 1, neon 3s1. So what it's saying is sodium has an electron configuration just like neon. There's neon's electron configuration. And you just add a 3s1 to it. So this is abbreviated configuration for sodium. Let's try another one. Let's say I wanted to do chlorine. So chlorine's electron configuration is 1s2, 2s2, 2p6, 3s2, 3p5. If we wanted to write the abbreviated version, the nearest noble gas before chlorine is still neon, right? So I'm going to write again neon, and chlorine has the exact same electron configuration as neon until you get to the valence electrons, which is 3s2, 3p5. All right, one more topic to go. We're going to talk about something called exceptional configurations. So a few of the atoms in the D block do not follow the Aufbau principle. Remember, Aufbau said that electrons fill the lowest energy levels first till they're full and then move up and up. Okay, so remember that atoms want the most stable configuration. I mean, that's the whole point. And normally, in most cases, the most stable configuration is when the electrons are in the lowest possible energy level. However, there are two other cases which make things very stable. If you have a completely full energy level, or if you have half full energy levels, like completely exactly half full, not partially full, but half full, okay? So there are two times when this could happen. One time is if you end in, if you're doing electron configuration, you end in S2D4. So let's do that real quick. And I'm actually going to do it with the orbital diagram. It's a little bit easier to see. So we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. Okay, so this is not the most stable because you've got one full sublevel and then a partially full sublevel. But with the movement of one electron, if I were to take this electron and move it to here, we now have a perfectly half-filled energy level. Okay, so I'll get rid of this guy. And you have a much happier atom. Okay, so anytime you're doing electron configuration or orbital diagram and you get the answer something S2, something D4, then move the electron to make it, what do I have D1 there? Should be S1D, change that, change this to D5, okay? That's a complete, that's when you have a complete half, how do I say this? You have a completely, perfectly half-filled energy level. Okay, the next time is if you have S2D9. The electrons are actually happier, the atom's actually happier if we have a full D, to just jump an electron over. So this is just something you sort of need to memorize. All right, that's it for today. Have a good one.